Welcome to this explainer. We're about to unlock what I can only describe as an incredibly elegant mathematical masterclass. We're going to take a journey that translates discrete matrix combinatorics, essentially grids of strictly whole numbers, specifically focusing on Hadamard's maximal determinant problem, into the flowing, continuous realms of quantum physics and geometric topology. It's a remarkable translation of mathematical languages, and as we'll see, it's all supported by some truly beautiful equations.
All right, let's jump right into the thick of it. The classic Hadamard determinant problem asks a deceptively simple question. What is the maximum possible determinant of an n by n matrix where every single entry is strictly a +1 or a -1? Now, when your dimension n is perfectly divisible by 4, everything is great. A perfect Hadamard matrix exists, hitting the absolute upper bound of n to the power of n over 2. But for dimensions not divisible by 4, a perfect orthogonal grid is topologically blocked. The mathematical structure literally fractures.
So that sets up a pretty wild contrast, doesn't it? The unramified dimensions, those perfectly divisible by 4, easily and seamlessly hit that absolute upper bound. But the frustrated dimensions, where n is congruent to 1, 2, or 3 modulo 4, leave us with a deeply fragmented puzzle. Finding the exact maximal determinant suddenly shatters into a nonlinear optimization problem, yielding things like the Barba bound or the Elik-Chatowski bounds. It turns from a smooth calculation into an entry-by-entry combinatorial nightmare. To get to the bottom of this and solve it properly, our derivation journey is going to cover 6 key steps. 1. The maximal determinant problem. 2. The Adelic moduli mapping. 3. Evaluating local epsilon factors. 4. Deriving the Barbaro bound. 5. The spectral action principle. And finally 6. Quantum error correction theory. Step 1. The maximal determinant problem, translating the discrete to the global. Think of this specific framework as our mathematical Rosetta Stone. It translates our discrete matrix problem entirely into the language of arithmetic geometry. So instead of a brute force search for plus or minus 1 matrix entries, we translate the problem itself. The matrix determinant becomes a global volume integration of the Arikov top form. The Hadamard bound, that becomes the absolute saturation of an unramified global L function. And those frustrating dimension discrepancies become mandatory activations of local Swan conductors. We're no longer guessing entries. We're looking for a globally rigid Hecke eigensheaf that minimizes spectral friction.
Moving on to step 2, the Adelic moduli mapping, lifting the matrix to the Adele ring. By lifting the matrix using J-theory, we completely transform the problem. The discrete matrix determinant actually maps directly onto the evaluation of the global Arikov metric volume element. Looking at the integral equation here, the absolute value of the determinant of m is perfectly equal to the integration over the moduli stack of the Arikov top form of a Hecke eigensheaf. We've essentially taken a rigid, discrete grid and turned it into a smooth, integrable topological surface.
Step 3. Evaluating local epsilon factors, the volume scaling formula. Here's where it gets really interesting. We have to calculate exactly how much that metric volume is forced to contract when we can't have perfect orthogonality. The overarching equation tells us that the maximum attainable volume, our determinant, is strictly bounded by a baseline scale factor C of n, multiplied by the inverse product of local epsilon factors evaluated at the central critical point where S equals 1/2. Essentially, these epsilon factors quantify the exact phase scrambling depth that physically contracts our volume away from that perfect Hadamard upper bound.
To solve that product, we actually evaluate across 3 distinct sectors. For the unramified sector, the factor is just 1. Easy enough. But in the exceptional finite sector, arithmetic friction isolates a specific prime number, causing a step-up. This forces the local root number to collapse onto a very specific obstruction, 1 over the square root of 2n minus 1. And finally, the Archimedean sector gives us the square root of n minus 1, which happens due to a fractional phase imbalance. Step 4. Deriving the Barba bound mathematical cancellation. When we assemble the global product by multiplying our 3 sectors together, a truly beautiful mathematical cancellation occurs. By separating the powers of the base term, the square root of n minus 1 in the numerator perfectly cancels the Archimedean phase shift of the square root of n minus 1 in the denominator. It's just brilliant. This elegantly locks in the exact numerical convergence of the classical Barba bound, the square root of 2n minus 1 times n minus 1 to the power of n minus 1 over 2. The geometry flawlessly recreates the discrete bound.
Step 5. The spectral action principle, physics and forces.
Now you might be wondering, if this moduli space is continuous, What fundamental physical action clamps the matrix entries strictly to a binary positive or -1? Why doesn't the field just take on fractional values to maximize its own volume? Well, the answer lies in the extended spectral action functional. This equation meticulously balances the kinetic spectral action, structural constraints, and crucially, a top-form volume maximizing potential. Scaled by gamma, which acts kind of like a continuous outward pressure, this potential pulls the eigenvalues of the system outward toward infinity, desperately trying to expand the hypercube. But here's the tension and release. In the explicit binary forcing equation, as that continuous pull tries to force the eigenvalues to infinity, it spikes the local Swan conductors. This intense arithmetic friction generates a massive, counter-restricting current in the localized stress-energy tensor. It forces the internal commutator to collapse into a rigid algebraic polynomial, 5x squared minus the identity matrix equals 0. The field literally snaps into a solid binary state, forcing the entries to clamp strictly at plus or -1. No fractions allowed. And finally, step 6, quantum error correction theory, spatial volume as logical information. Bringing this all back to quantum computing, this means maximizing our spatial matrix determinant under binary sign constraints is mathematically perfectly equivalent to maximizing your system's logical information capacity, the Shannon entropy, of a topological quantum lattice code, all while minimizing its syndrome entropy, which is its noise footprint. So how does that non-Hadamard structural block actually manifest in the physical world? Well, it shows up as an anionic defect, essentially a phase slip on the quantum lattice. That exact Swan conductor blowout we calculated earlier injects a discrete quantum of syndrome entropy, equal to the natural log of 2n-1, completely permanently inflating the noise footprint and permanently capping the code's logical capacity. This final equation proves that the natural log of the determinant of m is precisely equal to the logical information capacity of the topological code. It proves that finding the maximal determinant matrix for any dimension is mathematically identical to finding the exact number of orthogonal, non-interfering logical qubit channels embedded within a frustrated topological code. The classical Barba determinant formula is literally just an exponentiated information capacity threshold. Mind-blowing, right? I want to leave you with a rather profound realization from the source text. The discrete max-det matrices we've been trying to solve entry by entry for decades are simply the stable, macroscopic shadows cast by a quaternionic spacetime fabric maximizing its own structural volume under error-correcting constraints. It really makes you wonder, are the discrete mathematical bounds we study across all of mathematics merely the macroscopic shadows of an error-corrected universe desperately trying to maximize its own space-time volume?